Imagine staring up at the night sky, tracing the constellations with your eyes, and suddenly feeling that deep, almost electric sense of wonder. What if everything we see, everything we know, began in a single, unimaginable moment? That moment, the Big Bang, isn't just a scientific theory, it's the story of us, of everything. And yet, for all we think we understand about the birth of the universe, there are secrets hidden in the fabric of space itself, waiting to be uncovered. What if I told you that some of the most mind-bending discoveries about cosmic inflation, the explosive expansion of the universe in its earliest moments, have only come to light in recent years? These aren't just abstract ideas, they rewrite our understanding of reality, challenge our deepest assumptions, and reveal a cosmos far stranger and more magnificent than we ever dared to dream. Think about this for a second. The entire universe, all the galaxies, stars, and planets, even the very atoms in your body, were once compressed into a space smaller than a single grain of sand. Then, in less time than it takes to blink, the universe expanded faster than the speed of light, stretching and cooling until it became the vast, shimmering tapestry we see today. But here's the thing: scientists didn't just stumble upon this revelation. It took decades of painstaking observation, brilliant theories, and some of the most sophisticated technology ever built to piece together this cosmic puzzle. And what they've found is nothing short of revolutionary. From ghostly echoes of the Big Bang itself to the mind-bending concept of multiverses bubbling into existence, these discoveries don't just change textbooks, they change how we see our place in the grand scheme of things. That's exactly what we're diving into today: 25 incredible discoveries about the Big Bang and cosmic inflation that will leave you awestruck. Some of these findings confirm what we've long suspected, while others are so bizarre they sound like science fiction. But every single one is backed by cutting-edge research, from the faint whispers of primordial gravitational waves to the mysterious dark energy that's still pushing the universe apart. This isn't just a history lesson, it's a front-row seat to the greatest detective story ever told, where the clues are written in the stars and the detectives are the brilliant minds who have dedicated their lives to unraveling the universe's greatest mysteries. So if you've ever looked up at the sky and wondered how it all began, stick around, because what you're about to discover might just change the way you see everything. One of the most pivotal breakthroughs in modern cosmology came from a seemingly mundane source, a persistent hiss in a radio antenna that two scientists just couldn't seem to eliminate. In 1964, Arno Penzias and Robert Wilson were working with a highly sensitive horn-shaped antenna at Bell Labs in New Jersey, originally designed to study satellite communications. But no matter how carefully they adjusted their equipment, an eerie, unchanging hum persisted in their readings. They even cleaned out pigeon nests and droppings from the antenna, thinking the interference might be biological. Yet the noise remained, a whisper from the dawn of time itself. What they'd stumbled upon wasn't interference at all. It was the cosmic microwave background, the oldest light in the universe, a faint glow lingering from the Big Bang. This discovery was like finding a fossilized footprint of creation. The CMB is the cooled remnant of the universe's fiery birth, stretched over billions of years into microwaves by the expansion of space. It blankets the entire cosmos, bathing every direction in a nearly uniform sea of radiation just a few degrees above absolute zero. But here's what makes it so extraordinary: its near-perfect uniformity. No matter where you look, the temperature varies by less than 0.01%. That might sound insignificant, but it tells us something profound about the universe's infancy. For the cosmos to be so smooth, it must have undergone a period of unimaginably rapid expansion, cosmic inflation, flattening out any wrinkles in space-time like a balloon stretched to cosmic proportions. Yet the CMB isn't completely uniform. Tiny fluctuations in its temperature, mapped in exquisite detail by satellites like COBE and Planck, reveal the seeds of all structure in the universe. Those minuscule variations in density, some regions slightly hotter, others cooler, became the gravitational wells where galaxies and galaxy clusters would eventually form. It's as if we're staring at a baby picture of the cosmos, where the faintest ripples foretell the birth of stars, planets, and ultimately us. Without this primordial blueprint, the universe would be a featureless void. The CMB doesn't just confirm the Big Bang. It's a time capsule holding clues to how everything we know came to be. Penzier's and Wilson's accidental revelation earned them a Nobel Prize, but its true significance goes far beyond awards. The cosmic microwave background is our most direct link to the universe's first moments, a silent witness to the event that set everything in motion. And as technology advances, we're still decoding its secrets, peeling back layers of cosmic history written in microwaves. Every subtle anomaly, every faint pattern, tells us more about the forces that shaped reality. So the next time you hear static on an old television set, remember, some of that noise might just be the distant echo of the universe's birth, reaching across 13.8 billion years to remind us where it all began. But if the cosmic microwave background was our first glimpse of the Big Bang's aftermath, Alan Gut's inflationary theory was the revelation that explained why the universe looks the way it does. Picture this: in the late 1970s, Guth, then a young physicist at Stanford, was wrestling with two cosmic mysteries that shouldn't have existed. The first was the horizon problem. Why does the CMB look almost identical in opposite directions of the sky, when light wouldn't have had enough time to travel between those regions? The second was the flatness problem. Why does the universe appear so perfectly balanced between expansion and collapse, like a pencil standing on its tip for billions of years? Guth's eureka, a moment came when he realized these puzzles had the same solution: a runaway expansion in the universe's first moments. Imagine blowing up a balloon a trillion times in less than a trillionth of a second. That's cosmic inflation. Space didn't just expand, it exploded outward faster than light itself, smoothing out irregularities and stretching the fabric of reality until it became nearly flat. The horizon problem vanished because regions now separated by vast distances were once close enough to equalize their temperature. The flatness problem dissolved because inflation acted like an artist stretching a crumpled canvas until every wrinkle disappeared. What's truly staggering is the scale of this expansion. In just 10 to the minus 36 seconds, the universe grew by a factor of 10 to the 26. That's a 1 followed by 26 zeros. To put that in perspective, if the pre-inflation universe was the size of a marble, it would have become larger than the observable universe in that blink of time. And the driving force behind it, a mysterious energy field called the inflaton, which briefly dominated the cosmos before decaying into the particles and radiation we know today. But inflation isn't just a clever fix for theoretical problems. It makes testable predictions. It explains why we see those tiny fluctuations in the CMB, quantum ripples amplified to cosmic scales. It even suggests the mind-bending possibility that our universe is just one bubble in a froth of infinite universes, each with its own laws of physics. Guth's scribbles on a notepad didn't just solve old puzzles, they opened doors to realities we're still struggling to comprehend. And as experiments continue to hunt for primordial gravitational waves, the faintest echoes of inflation's tremors, we might soon have the ultimate proof that our universe began with the most spectacular growth spurt imaginable. Those tiny quantum ripples that Alan Guth's inflation theory predicted weren't just mathematical abstractions, they were the building blocks of everything. Picture the universe in its first moments, a seething cauldron of energy where the rules of quantum mechanics governed the impossible. At this scale, empty space wasn't truly empty. Particles flickered in and out of existence, their fleeting lives dictated by the uncertainty principle. These were quantum fluctuations, microscopic wrinkles in the fabric of reality, so small they'd vanish in an instant under normal circumstances. But inflation didn't just stretch space, it froze those quantum hiccups into the cosmic blueprint, magnifying them from subatomic quirks into the gravitational seeds of galaxies. Here's how it happened. As space expanded exponentially, those infinitesimal density variations, regions where matter was ever so slightly more or less concentrated, got stretched across the cosmos like fingerprints pressed into wet clay. The overdensities became gravitational anchors, pulling in surrounding matter over billions of years. Meanwhile, the underdense regions expanded into vast cosmic voids. The patterns we see in the CMB, those are the fossilized imprints of these quantum tremors, snapshots of the universe's texture when it was just 380,000 years old. It's staggering to think that the grand tapestry of galaxies, each with hundreds of billions of stars, traces back to random subatomic jitters magnified to cosmic proportions. What's even more remarkable is how precisely this process matches our observations. Satellite missions like Planck have mapped the CMB's temperature variations with extraordinary detail, revealing a near-perfect match to the predictions of quantum fluctuations stretched by inflation. The math is uncanny. The statistical distribution of hot and cold spots aligns with what you'd expect if tiny quantum noise had been blown up to astronomical scales. This isn't just a theory, it's a cosmic fingerprint, evidence written in microwaves that connects the quantum realm to the structure of the universe. Consider the implications. Without these quantum ripples, gravity would have had nothing to work with, no denser regions to collapse into stars, no scaffolding for galaxies to form. The universe would have remained a featureless soup of particles, cold and dark forever. But inflation turned microscopic randomness into cosmic destiny, ensuring that matter wouldn't be spread perfectly smooth. Those fluctuations were the universe's way of giving itself texture, creating the gravitational wells where gas could collect, stars could ignite, and planets could coalesce. In a very real sense, the spiral arms of the Milky Way and the vast walls of galaxy superclusters are the grown-up versions of quantum whispers from the dawn of time. Yet mysteries remain. Why did these fluctuations follow such a specific pattern? What determined their initial amplitude? Some theories suggest deeper layers of quantum gravity at play, or even connections to string theory's hidden dimensions. As we refine our measurements of the CMB's polarization, a potential window into gravitational waves from inflation, we might uncover whether these fluctuations were truly random or if some deeper order guided them. Either way, the story they tell is humbling. The largest structures in existence owe their existence to the smallest, most fleeting phenomena nature allows. And that revelation, that quantum mechanics wrote the first draft of cosmic history, might be one of the most profound discoveries of all. In 2014, the astronomy world erupted with excitement when researchers working with the BICEP 2 telescope at the South Pole announced they'd found something extraordinary. The first direct evidence of primordial gravitational waves etched into the cosmic microwave background. These weren't just any ripples in space-time. They were thought to be the echoes of cosmic inflation itself, a smoking gun for the universe's explosive birth. The team had detected a distinct swirling pattern in the polarization of the CMB, known as B modes, which seemed to match predictions of how inflation's gravitational waves would stretch the fabric of reality. For a brief, electrifying moment, it felt like science had touched the very moment of creation. The implications were staggering. If confirmed, this discovery wouldn't just validate inflation, it would open a window into energies 1 trillion times higher than what particle accelerators can reach, offering clues about how gravity and quantum mechanics intertwine at scales beyond imagination. Theorists scrambled to refine their models, and headlines proclaimed a new era of cosmology. But science has a way of tempering euphoria with scrutiny. Other researchers quickly pointed out a potential complication: interference from cosmic dust in our own galaxy. The Milky Way is filled with magnetically aligned dust grains that can produce similar polarization patterns, mimicking the signal bicep 2 claimed as primordial. As teams combined data from the Planck satellite and later observations, the initial optimism faded. The telltale B modes, it turned out, could largely be explained by this galactic dust. What once seemed like a definitive discovery became a cautionary tale about the challenges of peering back to the universe's first instance. Yet even in disappointment, there was progress. The episode sharpened our techniques for distinguishing between local interference and genuine primordial signals, refining the hunt for gravitational waves. Future experiments like the next-generation CMB observatories now have clearer roadmaps for separating cosmic whispers from galactic noise. The Bicep 2 story underscores a deeper truth about how science unfolds not in straight lines, but through fits, starts, and recalibrations. While the gravitational wave detection wasn't confirmed, the pursuit reshaped our understanding of what's possible. It reminded us that the universe guards its deepest secrets fiercely, and that every claim, no matter how thrilling, must survive the gauntlet of skepticism. Yet the possibility remains somewhere in the faint polarization of ancient light. The tremors of inflation may still be hiding, waiting for the right tools, the right moment to reveal themselves. And when they do, it could rewrite our story of reality once again. One of the most astonishing revelations about the early universe comes from an unexpected place: the geometry of space itself. Thanks to ultra-precise measurements of the cosmic microwave background, we've discovered something that defies everyday intuition. On cosmic scales, our universe is flat. Not flat like a sheet of paper, but in the sense that parallel lines never converge or diverge, and the angles of a triangle always add up to exactly 180 degrees. This isn't just a mathematical curiosity, it's a direct consequence of cosmic inflation, and it holds the key to understanding why our universe looks the way it does. Think about a balloon inflating to enormous size. As it stretches, any small curvature it once had becomes imperceptible, just as Earth's surface feels flat to us despite being a sphere. Inflation did the same to the universe, stretching space so dramatically that any original curvature was smoothed out to near-perfect flatness. But here's where it gets even more fascinating. This flatness isn't just about shape. It reveals a precise cosmic balancing act between matter, energy, and the expansion rate of the universe. If there had been even a slight deviation from this equilibrium, a fraction more matter or a tad less energy, the universe would have either collapsed in on itself long ago or expanded so rapidly that galaxies never formed. This delicate balance hinges on two enigmatic players, dark matter and dark energy. Dark matter, making up about 27% of the universe, acts as the invisible scaffolding that holds galaxies together. Without its gravitational pull, stars would fly apart. Dark energy, constituting 68%, is the mysterious force driving the universe's accelerated expansion. Together, along with ordinary matter, the stuff we're made of, they add up to just the right density to maintain that critical flatness. The CMB's temperature fluctuations, mapped with breathtaking precision, serve as the ultimate proof. When scientists analyzed these patterns, they found no detectable curvature. Space behaves like a perfect Euclidean plane on the grandest scales. But why does this matter? Because flatness is more than a geometric quirk. It's a time capsule from the universe's first moments. Inflation's rapid expansion didn't just flatten space. It locked in a specific ratio of matter to energy, a ratio that has persisted for billions of years. The fact that we observe this today is like finding a fossil preserved in perfect condition, untouched by time. And it raises profound questions. Was this balance inevitable, or is our universe one of many with different geometries? Some theories suggest that without inflation's fine-tuning, life as we know it couldn't exist. So when we measure the universe's flatness, we're not just studying space, we're uncovering the very conditions that made our existence possible. Yet mysteries linger. Dark energy's nature remains elusive. Why does it dominate now, after billions of years of matter's gravitational dominance? Could the universe's flatness hint at deeper connections between these invisible components? Future observations, like those from next-generation CMB experiments, may reveal subtle deviations or confirm inflation's predictions with even greater precision. Either way, the flatness of the universe stands as one of cosmology's most elegant discoveries, a silent testament to the forces that shaped reality from its explosive beginnings. And it reminds us that sometimes the most profound truths are hidden in the simplest geometry, written not in the stars, but in the very fabric of space itself. Hidden in plain sight among the cosmos' grandest mysteries is a number that shouldn't be causing this much trouble: the Hubble constant. This single value, representing how fast the universe expands today, has become the epicenter of a growing crisis in cosmology. Here's the problem: when scientists measure the expansion rate using two different methods, they get answers that stubbornly refuse to agree. One approach relies on the cosmic microwave background, the afterglow of the Big Bang, painstakingly mapped by satellites like Planck. The other method uses pulsating stars called Cepheids and exploding supernova in nearby galaxies as cosmic yardsticks. Both techniques are extraordinarily precise, yet they disagree by about 10%, a gap that's persisted despite decades of refined measurements. This isn't just a rounding error, it's a full-blown tension threatening to upend our most fundamental assumptions about cosmic history. Why does this discrepancy matter so much? Because the Hubble constant isn't just a speedometer for the universe, it's woven into everything from the age of the cosmos to the nature of dark energy. If the CMB measurements are correct, the universe should be expanding at roughly 67 kilometers per second per megaparsec. But observations of nearby stars and galaxies consistently peg the number closer to 73. At first glance, that difference might seem trivial, but in the finely tuned equations of cosmology, it's like discovering your car's speedometer and GPS disagree by 10% on a cross-country road trip. Either we're missing something enormous, or our understanding of the universe's evolution contains a critical flaw, the most tantalizing possibility. This tension could signal new physics beyond our current models. Maybe dark energy isn't constant as we've assumed, but evolves over time, subtly altering the expansion rate. Perhaps exotic particles from the early universe, like hypothetical dark radiation, left an imprint we haven't accounted for. Some theorists even speculate this could hint at flaws in Einstein's general relativity on cosmic scales, an idea that once seemed heretical but now demands serious consideration. The Hubble tension isn't just a measurement problem, it's a cosmic riddle challenging us to rethink the forces that have shaped reality since the first moments of inflation. What makes this debate so electrifying is how it pits two pillars of modern cosmology against each other. The CMB method reflects the universe's infancy, extrapolating forward based on our best models of cosmic inflation and dark energy. The local measurements, meanwhile, capture the universe as it is today, free from theoretical assumptions. That these approaches disagree suggests a crack in the foundation, a missing chapter in the story of how the universe grew from a fiery beginning to the vast, accelerating expanse we see now. Future telescopes, like the Nancy Grace Roman Space Telescope, aim to resolve this tension with even sharper observations. Until then, the Hubble constant remains cosmology's most intriguing paradox, a number simple in concept but profound in its implications, reminding us that the universe still guards its deepest secrets fiercely. Deep within the searing heat of the universe's first few minutes, a cosmic alchemy took place that would determine the very composition of everything to come. As temperatures cooled from quadrillions of degrees to mere billions, protons and neutrons began to fuse, forging the first atomic nuclei in a process called Big Bang nucleosynthesis. This brief window, lasting only about 17 minutes, created nearly all the helium in existence today, along with traces of deuterium and lithium. But here's what's extraordinary. The amounts predicted by theory match almost perfectly with what we observe in the oldest corners of the universe. It's as if the cosmos left us a receipt from its earliest transactions, and the numbers still add up billions of years later. Take helium, for example. About 25% of the ordinary matter in the universe is helium-4, the stable isotope with 2 protons and 2 neutrons. That's an astonishingly high abundance for an element that's barely produced in stars. The only explanation: it had to be forged in the Big Bang's furnace. Back when the universe was just 3 to 4 minutes old, temperatures dropped enough for neutrons and protons to stick together, forming deuterium, a heavy hydrogen isotope. These deuterium nuclei then collided and fused into helium at a rate so precise that today's measurements align with theoretical predictions down to a single decimal place. Even the tiny fraction of lithium-7 created during this process matches what we see in ancient stars, pristine relics from the cosmic dawn that haven't recycled their material through later generations. But the real test of any scientific theory lies in its predictive power. When physicists first calculated these elemental abundances based on the density of ordinary matter, they made a bold claim. If the Big Bang model is correct, the universe should contain about 1 deuterium nucleus for every 50,000 hydrogen atoms. Decades later, observations of distant gas clouds unchanged since the universe's infancy revealed a ratio of 1 in 52,000. That level of precision is like predicting the exact number of grains of sand on a beach and then counting them to confirm. What makes these light elements such powerful evidence is their sensitivity to the conditions of the early cosmos. The amount of deuterium we see, for instance, acts like a cosmic thermometer. Too many neutrons in the early universe, and deuterium would have fused away entirely. Too few, and stars would have burned through it long ago. The fact that we find just the right amount tells us the universe expanded and cooled at exactly the rate predicted by Big Bang physics. Similarly, the scarcity of lithium-7, only about 1 atom for every 10 billion hydrogen atoms, points to a universe where space stretched smoothly, without hidden pockets of turbulence that would have altered these delicate nuclear balances. Yet there's one intriguing wrinkle in this otherwise flawless story: the lithium problem. While deuterium and helium match predictions almost perfectly, the observed lithium abundance in ancient stars is about 3 times lower than theory suggests. Some researchers think this discrepancy might hint at unknown physics during nucleosynthesis, like exotic particles altering fusion rates. Others propose that these primordial stars processed lithium differently than we've assumed. Whatever the explanation, this tiny anomaly reminds us that even our most robust theories have room for mystery, and that the universe's first few minutes might still hold secrets waiting to be decoded. What's truly breathtaking is how these elemental fingerprints connect us directly to the universe's birth. Every helium atom in a child's balloon, every trace of deuterium in Earth's oceans, carries the imprint of those first explosive minutes. They're not just elements, they're cosmic artifacts, proof that the story written in the stars began with a spectacular beginning we're still learning to read. And as astronomers peer deeper into primordial gas clouds and refine their nuclear models, these light elements continue to whisper the same truth. The Big Bang wasn't just an idea, it left receipts. Among the near-perfect agreements between Big Bang predictions and observations, the lithium problem stands out like a sore thumb, a puzzle so persistent it's made scientists question whether we're missing something fundamental about the universe's first moments. According to meticulous calculations, the nuclear reactions in those initial fiery minutes should have left behind about 1 lithium-7 atom for every 10 billion hydrogen atoms. But when astronomers peer at the oldest stars in our galaxy, celestial time capsules preserving primordial chemistry, they find only a third of that expected lithium. This discrepancy isn't just a minor accounting error. It's a cosmic anomaly that has sparked debates spanning particle physics, stellar astrophysics, and even alternative theories of gravity. One leading explanation digs into the exotic physics of the early universe. Could unknown particles, like certain types of dark matter, have altered nuclear reaction rates during nucleosynthesis? Some theories suggest weakly interacting massive particles, or WIMP, might have absorbed energy or disrupted proton-neutron balances, suppressing lithium production. Others propose that undiscovered forces temporarily influenced how nuclei fused in that seething primordial soup. If proven, these ideas wouldn't just solve the lithium problem, they'd open a backdoor to detecting physics beyond the standard model, hidden in the universe's oldest chemical fingerprints. Then there's the stellar angle. Ancient stars, though pristine compared to younger generations, aren't perfectly inert museums. Over billions of years, their churning atmospheres might have dragged lithium down into hotter interior layers where nuclear reactions destroyed it. Imagine a cosmic magician's trick. What if these stars didn't form with less lithium but somehow hid it from our telescopes? Observations of certain metal-poor stars show lithium depletion correlated with rotation rates, hinting at internal mixing processes. Yet even this elegant solution has gaps. Not all old stars show the same depletion patterns, and simulations struggle to explain the universal scarcity of lithium across diverse stellar populations. Perhaps the most radical possibility challenges our very understanding of Big Bang nucleosynthesis. Could space have been lumpy in those first minutes, with variations in density or temperature creating pockets where lithium formed differently? Or might gravitational effects from extra dimensions, a wild idea from string theory, have tweaked nuclear reaction pathways? These speculative solutions remind us how much we still don't know about the universe's birth. What makes the lithium problem so compelling is its stubborn refusal to fit neatly into our cosmic narrative. Unlike helium and deuterium, which align almost poetically with predictions, lithium throws a wrench into the works, forcing scientists to reevaluate assumptions. It's a reminder that even our most successful theories have unfinished chapters, and that the oldest stars in the sky might still be keeping secrets about how everything began. If you took all the stars, galaxies, and visible gas in the universe and put them on a cosmic scale, they'd barely register, like a sprinkle of glitter on a vast, dark canvas. The real architect of cosmic structure isn't the stuff we see, but something invisible and mysterious: dark matter. This enigmatic substance, which neither emits nor reflects light, makes up about 27% of the universe's total mass energy content. But its influence is everywhere, written into the very blueprint of reality. From the elegant spirals of galaxies to the colossal filaments of the cosmic web, dark matter's gravitational embrace has shaped everything we observe. Take galaxy rotation curves, one of the earliest clues that something was amiss in our understanding of the cosmos. In the 1970s, astronomer Vera Rubin noticed something bizarre about how stars orbit the centers of spiral galaxies. According to Newton's laws, stars on the outer edges should move slower than those near the center, just as planets farther from the Sun orbit more sluggishly. But Rubin's observations revealed the opposite. Stars at a galaxy's outskirts whizzed around just as fast as those closer in, as if some unseen mass was anchoring them in place. The only explanation: an invisible halo of dark matter extending far beyond the galaxy's luminous edge, providing the extra gravitational pull needed to keep those stars from flying off into the void. This discovery wasn't just a footnote in astrophysics, it overturned our entire picture of how galaxies form. Without dark matter's scaffolding, the universe would look radically different. Here's why. In the early cosmos, ordinary matter, protons, neutrons, and electrons, was too hot and energetic to clump together easily. But dark matter, unaffected by radiation pressure, began collapsing under its own gravity first, forming dense pockets called halos. These halos acted like gravitational traps, slowly pulling in ordinary matter until it cooled enough to form stars and galaxies. In essence, every galaxy we see today is just the luminous tip of a vast iceberg, embedded in a much larger nest of dark matter. Modern simulations, like the famous Millennium Run, illustrate this process with breathtaking detail. When scientists model the universe's evolution with dark matter as the driving force, they see filaments of invisible matter stretching across billions of light years, intersecting at dense nodes where galaxies cluster. This cosmic web matches precisely what we observe in galaxy surveys, a sprawling, interconnected architecture where luminous matter traces the underlying dark skeleton. The agreement between simulations and observations is so precise that it's hard to imagine any alternative explanation holding up. Yet dark matter's role goes beyond just sculpting galaxies. It also solves one of the universe's great timing problems. After the Big Bang, ordinary matter was ionized, a plasma so hot it scattered light relentlessly. Only after 380,000 years, when atoms finally formed, could photons travel freely, creating the CMB we see today. But for galaxies to arise so soon after this cosmic dawn, gravity needed a head start, something to begin pulling matter together before atoms even existed. Dark matter provided that crucial early push, seeding structures that would later blossom into the galaxies we know. The irony is profound. The very stuff that makes up most of the universe's mass is also the most elusive. We still don't know what dark matter is, whether it's a yet undiscovered particle, a modification of gravity, or something even stranger, but its gravitational fingerprints are undeniable. From the spin of galaxies to the bending of light around galaxy clusters, a phenomenon called gravitational lensing, the evidence is woven into the fabric of the cosmos. What's next? Scientists are hunting for dark matter particles with detectors buried deep underground, shielded from cosmic noise. Others are searching for subtle distortions in the CMB that might reveal dark matter's interactions in the early universe. Whatever we discover, one thing is certain: dark matter isn't just a passive ingredient in the cosmic recipe, it's the invisible hand that shaped the universe into the rich, structured tapestry we call home. And unlocking its secrets might just rewrite our understanding of reality itself. In 1998, two teams of astronomers made a discovery so shocking it turned cosmology on its head. They proved the universe isn't just expanding, but accelerating. This wasn't a subtle tweak to existing theories. It was like throwing gasoline on the fire of cosmic mysteries. By meticulously studying distant supernova stellar explosions so uniform they serve as cosmic mile markers, the teams found that these beacons were dimmer than expected, meaning space had stretched more than anyone predicted. The implication: some invisible force is pushing galaxies apart faster and faster. A revelation so profound it earned researchers the Nobel Prize just 13 years later. This force, dubbed dark energy, is perhaps the most baffling discovery in modern physics. Think of it like this: if gravity is the universe's brakes, dark energy is its accelerator pedal, pressed relentlessly for billions of years. What makes it even stranger is its eerie resemblance to the repulsive gravity that drove cosmic inflation. During the universe's first trillionth of a second, a similar anti-gravitational effect ballooned space to unimaginable scales before vanishing. Now, dark energy seems to be reigniting that ancient process, but at a far gentler pace, stretching the cosmos not in an instant, but over eons. Yet dark energy's nature remains one of science's greatest enigmas. The leading candidate, called the cosmological constant, suggests it's an inherent property of space itself, a sort of energy woven into the vacuum. Every cubic centimeter of emptiness, according to this idea, contains a tiny amount of repulsive force. But here's the catch: when physicists calculate how strong this energy should be based on quantum theory, their predictions overshoot observations by a factor of 10 to the power of 120. That's the worst mismatch in science history, a discrepancy so vast it hints we're missing something fundamental about how reality works. Alternative theories abound. Maybe dark energy isn't constant but evolves over time, a concept called quintessence. Or perhaps it signals a flaw in Einstein's gravity theory, requiring modifications on cosmic scales. Some even speculate it's linked to parallel universes in a vast multiverse, where different regions exhibit different expansion rates. The stakes couldn't be higher. Dark energy determines the universe's ultimate fate. If it strengthens, we could face a big rip, where galaxies, stars, and even atoms are torn apart. If it weakens, gravity might regain dominance, collapsing the cosmos in a fiery, big crunch. What's certain is this: dark energy's discovery forced us to confront how little we understand about the universe's architecture. It's as if we've spent centuries studying a house's walls and furniture, only to realize the foundation is made of something we can't see or explain. And just like inflation's repulsive gravity shaped the early universe, dark energy is sculpting our cosmic future, a silent, invisible hand rewriting the story of everything. Now, as next-generation telescopes like the Vera Rubin Observatory and Euclid Space Mission map the universe's expansion with unprecedented precision, we stand on the brink of another revolution. Will dark energy remain steady, or does it fluctuate? Does it interact with dark matter, or is it entirely separate? Each observation chips away at the mystery, inching us closer to answers that could redefine physics itself. One thing's clear: the universe still has surprises up its sleeve, and the greatest chapters in this cosmic detective story may be yet to come. The cosmic microwave background should be the ultimate cosmic democracy, a snapshot of the early universe where hot and cold spots are scattered randomly with no preferred direction or alignment. But in 2005, astronomers stumbled upon something that defied this expectation. A bizarre pattern in the CMB's fluctuations that seemed to eerily align with our solar system's plane. Dubbed the axis of evil, this anomaly suggests the universe might have a preferred direction, a cosmic axis that, if real, would upend our most fundamental assumptions about the Big Bang. Imagine spinning a globe and realizing all the continents point in the same direction. That's the level of strangeness we're dealing with. The CMB's quadrupole and octupole moments, the way its temperature variations are distributed, aren't as random as they should be. Instead, they appear to align with the ecliptic, the plane where Earth and the other planets orbit the Sun. This shouldn't happen. According to the cosmological principle, the universe has no special place or direction. Matter and energy are spread uniformly on large scales. The axis of evil challenges that bedrock idea, hinting that either our universe has a hidden architecture or something very peculiar is skewing our observations. Some theorists suggest this could be evidence of new physics, perhaps relics from before the Big Bang, like cosmic strings or defects in space-time left over from a more exotic birth of the cosmos. Others propose it might reflect a deeper connection between the quantum vacuum and the large-scale structure of the universe, a shadow of inflation's quantum origins written into the CMB. The wildest ideas even entertain the possibility that we're seeing imprints from a colliding bubble universe, a multiverse encounter frozen in the microwave sky. But before we rewrite cosmology textbooks, there's the sobering possibility of observational bias. Could this alignment simply be an artifact of how we measure the CMB? Our solar system isn't perfectly motionless, it's moving through space at about 370 kilometers per second relative to the CMB's rest frame. This motion creates a Doppler effect, stretching light slightly in one direction and compressing it in another, which might subtly skew our perception of the CMB's patterns. There's also the challenge of foreground contamination, dust and radiation from our own galaxy that could be distorting the signal in ways we haven't fully accounted for. Yet, even after meticulous analysis, the axis of evil refuses to disappear entirely. Planck satellite data, the most precise CMB measurements to date, still show residual correlations between the ecliptic and the CMB's large-scale fluctuations. The statistical significance isn't overwhelming, about a 1 in 1,000 chance of being random noise, but in cosmology, where margins of error are razor-thin, that's enough to keep scientists debating. The anomaly forces us to ask uncomfortable questions. Is the cosmological principle incomplete? Does the universe have a subtle anisotropy we've missed? Or is this simply the universe playing tricks on us, a cosmic coincidence that will dissolve with better data? Future experiments like next-generation CMB observatories with even finer resolution may finally settle the mystery. But for now, the axis of evil stands as one of cosmology's most tantalizing loose ends, a whisper that the universe might not be as uniform as we thought, and that the story of the Big Bang could still hold surprises in its oldest light. Whether it's a flaw in our models or a crack in the foundations of reality, one thing's certain: the cosmos still has secrets to share. Buried in the cosmic microwave background, like a ghostly fingerprint from another reality, lies one of the universe's most perplexing anomalies, the cold spot. Stretching nearly 2 billion light-years across, this mysterious region in the constellation Eridanus is significantly colder than its surroundings, as if a cosmic freezer door had been left ajar in the early universe. At first glance, it might seem like a statistical fluke, just another random fluctuation in the CMB's sea of hot and cold patches. But the odds of such an extreme cold area appearing by chance? Less than 1 in 50. This isn't just a curiosity, it's a screaming outlier that demands explanation, and the theories proposed to account for it are as wild as they are revolutionary. One leading idea involves cosmic textures, exotic defects in space-time left over from the universe's earliest moments. Picture the infant cosmos cooling from an unimaginably hot, symmetric state, like molten metal solidifying into a crystalline structure. Just as cracks can form in cooling metal, the fabric of reality might have developed topological imperfections as it transitioned. These textures, if they exist, would warp space-time around them, altering how light travels and creating cold spots in the CMB. It's an elegant solution, but here's the catch. No one has ever detected direct evidence of these hypothetical structures. The cold spot could be our first clue that they're out there, hidden in the cosmic background like fossils from a more exotic era. Then there's the far more radical possibility the cold spot might be a bruise from a collision with another universe. In the multiverse scenario, our cosmos is just one bubble in an infinite froth of universes, each with its own physics. If another bubble brushed against ours during inflation, the energy released at the boundary could have left a distinct imprint, an unusually cold, empty region. Imagine 2 soap bubbles gently touching. The spot where they meet would distort, creating a dimple. That's essentially what some theorists suggest happened on a cosmic scale, with the cold spot as the aftermath. If true, this wouldn't just solve a CMB anomaly, it would be the first empirical evidence that parallel universes exist, but not everyone's convinced. Skeptics argue the cold spot might have a more mundane origin, like a supervoid, an enormous, underdense region of space where fewer galaxies and less matter pull light from the CMB, subtly cooling it through a phenomenon called the integrated Sachs-Wolf effect. Surveys have indeed found a sparse region roughly aligned with the cold spot, but there's a problem. The void isn't nearly large or empty enough to explain the temperature drop. It's like blaming a puddle for flooding a city. The scale doesn't add up. What makes the cold spot so electrifying is its refusal to fit neatly into any box. Whether it's evidence of new physics, a multiverse collision, or something we haven't even imagined yet, it challenges the comforting idea that we've got the cosmic story figured out. Future telescopes, like the European Space Agency's Euclid mission, could settle the debate by mapping the distribution of galaxies around the cold spot with unprecedented precision. Until then, this icy enigma remains one of cosmology's great conversation starters, a cosmic Rorschach test where some see the shadow of another universe and others the birth pangs of our own. And that's the beauty of anomalies. They remind us that the universe is still writing its rulebook and we're just beginning to read it. Pinpointing the universe's age might seem like an impossible task. How do you date something that encompasses all of time and space? Yet through a combination of cosmic detective work and cutting-edge technology, scientists have narrowed it down to an astonishingly precise figure, 13.8 billion years. This number isn't just a rough estimate. It's the result of two independent lines of evidence converging with remarkable agreement, each reinforcing the other like cross-referenced alibis in a cosmic mystery. The first clue comes from the cosmic microwave background. By measuring the CMB's temperature fluctuations with satellites like Planck, researchers can essentially rewind the universe's expansion to its starting point. Think of it like calculating how long a cake has been baking by measuring how much it's risen and knowing the oven's temperature. The CMB reveals how fast the early universe expanded, how matter clumped together, and how these factors evolved over billions of years. Planck's data, combined with our understanding of dark matter and dark energy, delivers an age estimate so precise it feels almost audacious: 13.77 billion years, give or take a mere 40 million. But here's where it gets fascinating. A completely different method tracking the Hubble constant should, in theory, arrive at the same answer. By measuring how fast galaxies are racing apart today and extrapolating backward, astronomers can estimate how long this cosmic sprint has been going on. Supernova, Cepheid variable stars, and gravitational lensing of distant quasars all contribute to this calculation. The problem: depending on which local measurements you use, the universe's age sometimes comes out a tad younger or older than the CMB's verdict. This tension, though seemingly small, is like discovering your watch and your phone's clock disagree by just enough to make you question which one to trust. The discrepancy might seem trivial, a difference of less than 10%, but in cosmology, even tiny mismatches can hint at revolutionary discoveries. Some theorists speculate that dark energy's strength has changed over time, subtly altering the expansion rate in ways we haven't accounted for. Others wonder if unknown particles from the early universe, like sterile neutrinos, might have left an imprint on the CMB that skews our calculations. The most tantalizing possibility: that our measurements are revealing cracks in the standard cosmological model, suggesting the universe's history is more complex than we've assumed. What's incredible is how far we've come. A century ago, estimates of the cosmos's age ranged wildly from a few million to infinitely old. Even in the 1990s, uncertainty spanned billions of years. Now, thanks to missions like Planck and Hubble, we're arguing over decimal places. Yet the remaining uncertainties remind us that cosmology is a living science, still piecing together the story of everything. Every new telescope, every refined measurement brings us closer to understanding not just how old the universe is, but how it chose to grow up this way. The idea of a single universe might be too small to contain reality's full strangeness. What if our cosmos is just one bubble in an endless froth of universes, each with its own unique laws of physics? This is the multiverse hypothesis, a staggering offshoot of cosmic inflation that suggests the Big Bang wasn't a one-time event, but an endless cosmic assembly line, churning out universes with every passing moment. Eternal inflation, a twist on standard inflation theory, paints a picture where space doesn't just expand rapidly for a brief instant, it keeps ballooning forever in certain regions. Imagine a pot of water boiling violently with bubbles forming and popping at the surface. Now replace the water with spacetime itself and each bubble with an entire universe. In this scenario, our universe is just one bubble among countless others, each pinched off from the expanding quantum foam with its own random properties. Some might have stronger gravity, others might lack electromagnetism entirely. A few might even have extra dimensions crumpled up in ways we can't begin to visualize. What makes this idea so compelling is how neatly it solves one of cosmology's biggest puzzles: fine-tuning. Our universe's constants, the strength of gravity, the mass of electrons, even the density of dark energy are exquisitely balanced to allow for stars, planets, and life. The odds of this happening by chance seem vanishingly small unless there are infinite universes where every possible combination gets tried out. In that cosmic lottery, we just happen to live in one of the rare universes where the numbers came up right. It's like walking into a library containing every book ever written. Of course, you'd find one in your language because every possible variation exists somewhere. But how could we ever test something as outlandish as other universes? Surprisingly, there are potential fingerprints. If our bubble universe collided with another during inflation, the energy released might have left scars in the cosmic microwave background, oddly shaped cold spots or strange patterns in polarization. Some researchers even speculate that dark flow, the mysterious motion of galaxy clusters in a preferred direction, could be the gravitational tug of a neighboring universe. And if the multiverse is real, it might explain why dark energy's value seems so improbably small in our cosmos. In most universes, it's either zero or so large that galaxies never form. We're left with survivor bias, seeing only the rare habitable bubbles. Critics argue this sounds less like science and more like philosophy, untestable speculation dressed up in equations. But proponents counter that the same was once said about black holes and the Big Bang itself. The multiverse might always remain just beyond our observational reach, but as a framework, it's reshaping how we think about the origins of everything. After all, if inflation truly is eternal, then the universe we call home might be less a unique creation and more a single page in an infinite cosmic library, where every possible story, no matter how bizarre, is being written somewhere in the vastness beyond our cosmic horizon. The sudden halt of cosmic inflation is one of the universe's greatest vanishing acts. After stretching space by a factor of 10 to the 26 in less than a trillionth of a second, this explosive growth didn't just taper off, it collapsed in on itself, transforming into the seething plasma of the hot Big Bang. But how does something so violent and all-encompassing simply stop? The answer lies in a process called reheating, where the energy that powered inflation didn't disappear but instead decayed into the particles and radiation that would fill the young cosmos. Picture inflation as a ball rolling down a hill, gathering speed as it goes. The hill represents the inflattened field, the mysterious energy that drove space's exponential expansion. At the top, the field is stuck in a high-energy state, like a ball balanced precariously on a slope. This false vacuum keeps space expanding at an accelerating rate. But nothing lasts forever. Quantum fluctuations eventually nudge the inflattened field toward its lowest energy state, like the ball finally tipping over the edge. When it reaches the valley below, the energy stored in the field doesn't vanish. It erupts outward in a torrent of particles and heat. This moment, reheating, marks the Big Bang's fiery beginning, as the universe transitions from cold, empty expansion to a dense, ultra-hot soup of quarks, photons, and electrons. The mathematics behind this transition is dizzying. Calculations suggest the inflattened field oscillated wildly as it decayed, like a spring vibrating after being released. Each oscillation transferred energy to newly created particles, effectively reheating the universe from near absolute zero to temperatures exceeding 10 to the 27 degrees, hot enough to forge the first atomic nuclei. This wasn't a gentle warming but a violent rebirth, filling the stretched emptiness of inflation with the raw materials for everything to come. But reheating wasn't uniform. Tiny quantum fluctuations during inflation became variations in energy density during this phase, creating the seeds for galaxies and cosmic structure. Regions where the inflaton decayed slightly later remained cooler, while others reheated more vigorously. These imperfections, frozen into the fabric of space, would later grow under gravity's pull, sculpting the vast web of galaxies we see today. It's a staggering thought. The same randomness that shaped the cosmos's birth still echoes in the distribution of stars and voids billions of years later. The end of inflation also solved one of its own paradoxes. If space had kept expanding exponentially, matter would have been diluted to near nothingness, leaving the universe a vast, empty void. Instead, reheating concentrated energy back into localized pockets, allowing particles to collide, interact, and eventually form atoms. Without this phase, the universe would have remained a featureless desert. No stars, no planets, no life. Yet mysteries linger. Did inflation end everywhere at once, or did some regions keep expanding while others transitioned? Could bubbles of still inflating space exist beyond our observable universe? Some theories even suggest that reheating might have been incomplete, leaving behind relics like dark matter or hidden sectors of particles we've yet to detect. As physicists simulate these first moments on supercomputers, they're uncovering clues about how the universe's most violent beginning gave way to the structured cosmos we call home. What's clear is this: the end of inflation wasn't an ending at all. It was a cosmic metamorphosis, turning the energy of empty space into the matter and light that would build galaxies, stars, and us. And buried in the particles around us, in every atom, every photon might still be whispers of that moment when the universe took its first breath and began anew. Before galaxies, before planets, even before most of the elements on the periodic table existed, the universe was lit by pioneers of light, the first stars. These celestial giants, known as population 3 stars, were unlike anything we see today. Formed from the pristine hydrogen and helium forged in the Big Bang's nuclear furnace, they burned at temperatures so extreme they would make our sun look like a flickering candle. Current simulations suggest these stars were behemoths, some reaching up to 300 times the mass of our sun, with lifetimes measured in mere millions of years before exploding in spectacular supernova. The reason these stars were so different lies in the raw materials available to them. Without heavier elements like carbon or oxygen to help dissipate heat during formation, gas clouds could collapse into far denser, hotter cores. Imagine trying to build a fire with nothing but kindling, no logs, no dampers, just pure, unrestrained fuel. That's essentially what happened in the early universe. The lack of heavier elements allowed these stars to grow to staggering sizes, their nuclear fusion processes running at breakneck speeds. When they finally died, their violent death seeded the cosmos with the first heavy elements, scattering carbon, oxygen, and iron into the void, the building blocks for everything that followed, including us. But how do we know these stars existed if none survive today? The evidence is written in the oldest light we can observe. The cosmic microwave background shows us the universe's state before stars, while later observations reveal the epoch of reionization, a period when these first stars' intense ultraviolet radiation split neutral hydrogen atoms into protons and electrons, making the universe transparent to light. This transition, occurring a few 100 million years after the Big Bang, acts like a cosmic timestamp, marking the moment starlight began sculpting the cosmos. Even more tantalizing are the chemical fingerprints left behind. The oldest stars we've found in our galaxy population, 2 stars, contain trace amounts of elements heavier than helium, but in patterns that suggest they formed from the ashes of just 1 or 2 massive population 3 supernova. It's like finding pottery made with shards of an earlier, lost civilization. These ancient second-generation stars serve as cosmic archaeologists, preserving clues about their even older predecessors. The hunt for direct proof continues. Telescopes like the James Webb Space Telescope are peering back to the universe's infancy, searching for the telltale infrared glow of these first stars' galaxies. Meanwhile, astronomers listen for the faint echoes of their explosions in the form of gamma ray bursts, the most energetic event since the Big Bang itself. Each discovery inches us closer to understanding how the darkness of the early universe gave way to light, and how the first stars set the stage for the rich cosmic tapestry we see today. What's astonishing is how much we've pieced together without ever seeing these stars directly. Through simulations, chemical analysis, and the subtle imprints they left on the fabric of space, we've reconstructed their story, one of brilliance, brevity, and ultimate sacrifice. They were the universe's first alchemists, turning simplicity into complexity, darkness into light. And in their short, fiery lives, they laid the foundation for everything that came after galaxies, planets, and life itself. For hundreds of millions of years after the Big Bang, the universe was a cosmic fog, a vast expanse of neutral hydrogen gas so thick it absorbed nearly all ultraviolet light. Then something extraordinary happened. Between about 150 million and 1 billion years after the cosmic dawn, the first stars and galaxies switched on like beacons in the darkness, their intense radiation burning away the hydrogen fog in a process called reionization. This epochal transition didn't just light up the cosmos, it fundamentally reshaped it, transforming an opaque sea of atoms into the transparent universe we observe today. The evidence for this cosmic metamorphosis comes from two brilliant lines of investigation. The first involves quasars, supermassive black holes at the centers of young galaxies, blazing with enough energy to outshine entire galaxies. As their light travels through intergalactic space, it passes through clouds of neutral hydrogen that absorb specific wavelengths, creating dark absorption lines in the quasar spectrum. But here's the crucial detail: the farther away and thus older the quasar, the more complete these absorption features become, until around redshift 6, when the universe was roughly 1 billion years old, the lines suddenly weaken. It's as if a cosmic curtain was lifted, revealing a universe where hydrogen had been stripped of its electrons, becoming ionized plasma incapable of absorbing light in the same way. Meanwhile, the cosmic microwave background tells a parallel story through its polarization patterns. As the first stars and galaxies flooded the universe with ultraviolet radiation, the interaction between this light and free electrons created subtle swirls in the CMB's polarization, a phenomenon known as E-mode and B-mode polarization. The Planck satellite's painstaking measurements revealed these patterns match precisely what astrophysicists predicted for reionization occurring gradually between redshifts 20 and 6. Together, these independent lines of evidence paint a compelling picture. The universe didn't flip a switch from opaque to transparent, but underwent a messy, uneven transformation as ionizing bubbles grew around early galaxies, eventually overlapping to clear the cosmic fog entirely. What's astonishing is how much energy this required. The first stars, massive, short-lived, and unimaginably hot, were the primary drivers early on, their ultraviolet photons powerful enough to knock electrons clean off hydrogen atoms. Later, as galaxies grew more numerous, their collective radiation completed the job. But here's the puzzle. Current observations suggest there weren't enough small galaxies in the early universe to provide all the necessary ionizing photons. This photon underproduction crisis has led theorists to propose wild solutions. Perhaps early stars were even more efficient at producing UV light than we thought. Or maybe supermassive black holes contributed more than expected. Some even speculate about exotic particle decay or primordial black holes as additional ionization sources. The epoch of reionization wasn't just a historical curiosity, it set the stage for everything that followed. By making the universe transparent to ultraviolet light, it allowed galaxies to cool their gas efficiently, enabling the formation of smaller, longer-lived stars like our Sun. It also determined when we could begin observing the cosmos in its full glory. Without reionization, even today's most powerful telescopes would see only a dim, foggy glow. And as new instruments like the James Webb Space Telescope peer back to this pivotal era, we're catching glimpses of the very galaxies that burned away the darkness, their faint light stretched by cosmic expansion into infrared whispers from the dawn of time. What emerges is a story of transformation, not instantaneous but gradual, not uniform but chaotic. The universe didn't simply wake up one day and decide to become transparent. It fought its way out of the fog, photon by photon, star by star, until the light could finally travel freely across billions of years. And in those ancient photons, the ones that first pierced the darkness, we find the echoes of our cosmic awakening. Hidden within the cosmic microwave background's near-perfect smoothness is a ghostly rhythm, a pattern of faint ripples frozen in time. These aren't just random fluctuations, they're the fossilized echoes of sound waves that reverberated through the newborn universe, imprinting themselves on the distribution of galaxies we see today. Known as Baryon acoustic oscillations, these cosmic vibrations act like a ruler etched into the fabric of space, revealing secrets about the universe's composition, expansion, and even its ultimate fate. Picture the early universe just 400,000 years after the Big Bang. It's a seething plasma of protons, electrons, and light, so dense that photons can't travel far before colliding with particles. But within this hot soup, gravity is tugging matter inward while radiation pressure pushes outward, creating a tug of war that generates pressure waves, literal sound waves rippling through the cosmos. These waves traveled at nearly 2/3 the speed of light, compressing and rarefying matter like the crests and troughs of an ocean wave. Then, as the universe cooled and atoms formed, the music suddenly stopped. The waves froze in place, leaving behind concentric rings of slightly denser matter, like ripples around a pebble dropped in a pond. Fast forward billions of years, and those frozen ripples became the scaffolding for galaxies. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing a startling pattern. Galaxies are slightly more likely to be found about 500 million light-years apart, the exact scale of those ancient sound waves stretched by cosmic expansion. It's as if the universe left us a cosmic measuring tape with the BAO scale as its markings. This allows astronomers to track how the universe has expanded over time by comparing the apparent size of these oscillations at different distances. The farther back we look, the tighter those galaxy clusters should appear, since the universe hadn't stretched them as much. But BAOs do more than measure expansion. They're a forensic tool for weighing the cosmos. By analyzing how galaxies cluster around these oscillations, scientists can calculate the universe's total mass, including dark matter's invisible pull. The results consistently corroborate other measurements. Dark energy makes up about 68% of the cosmos, dark matter 27%, and ordinary matter, everything we can see, are just 5%. That ordinary matter is key. The baryon in baryon acoustic oscillations refers to protons and neutrons, the building blocks of atoms. The fact that we see their imprint so clearly confirms that dark matter, while dominant gravitationally, doesn't interact with light or sound waves the way ordinary matter does. Perhaps most astonishing is how precisely these ancient sound waves match theoretical predictions. Simulations of the early universe, when combined with our understanding of plasma physics, produce BAO patterns that align almost perfectly with observations. This convergence of theory and observation is one of cosmology's greatest triumphs, a direct link between the quantum fluctuations of inflation and the large-scale structure of the modern universe. Every galaxy supercluster, every vast cosmic void bears the subtle fingerprint of those primordial vibrations, yet mysteries remain. Why do some galaxy surveys show slight deviations from the expected BAO scale? Could there be unknown forces at play, or is it simply a matter of measurement precision? Future missions like the Dark Energy Spectroscopic Instrument aim to map tens of millions of galaxies, sharpening our view of these cosmic echoes. As we refine our measurements, we're not just studying sound waves, we're listening to the universe's first notes, a symphony of creation that still shapes the cosmos today. And in those faint vibrations, we find a rhythm that connects the smallest quantum fluctuations to the grandest structures in existence. The shape of the universe isn't just a philosophical question, it's a geometric puzzle with real consequences for how we understand reality. For centuries, we assumed space was infinite and flat, stretching endlessly in all directions. But what if the cosmos is actually finite, yet has no edges? Imagine a cosmic donut where traveling far enough in one direction would eventually bring you back to where you started, not because you've circled a globe, but because space itself loops in ways our three-dimensional brains struggle to visualize. This mind-bending possibility, known as a multiply-connected topology, suggests the universe could be far smaller than it appears, just cleverly folded in on itself. Scientists hunt for this hidden architecture in the cosmic microwave background. If space loops around like a video game screen where exiting one edge teleports you to the opposite side, those loops should leave faint fingerprints repeating patterns in the CMB's temperature fluctuations. Picture standing between two mirrors and seeing infinite reflections of yourself. Now replace the mirrors with the fabric of space-time, and your reflections with duplicate hot and cold spots in the microwave sky. Teams analyzing Planck satellite data have searched tirelessly for these ghost images, scanning the CMB for matching circles or statistically improbable correlations that would betray the universe's true shape. The simplest finite model, a 3 torus, would make the cosmos behave like a hall of mirrors in every dimension. Travel far enough east and you'd return from the west, ascend long enough and you'd reappear below. But the universe could also twist into more exotic forms, a dodecahedral space, for instance, where light wraps around in surprising ways, creating intricate patterns in the CMB. Some theorists even speculate about a Klein bottle topology, a shape with only one surface that turns inside out as it curves through higher dimensions. The challenge: these structures would imprint subtly different signatures, requiring exquisitely precise measurements to distinguish them from random noise. So far, the evidence is tantalizing but inconclusive. Some studies claim to spot matching circles in the CMB, while others found no statistically significant repeats. The Planck mission's final analysis leaned toward infinite flatness, but couldn't rule out compact topologies smaller than about 90 billion light-years. That might sound enormous, but it's a fraction of the observable universe's scale. Future CMB experiments with higher resolution could settle the debate, hunting for telltale correlations at finer angular scales. What's at stake isn't just a cosmic geometry quiz. A finite universe would rewrite our understanding of cosmology's biggest questions. Inflation might not have created an endless multiverse, but a carefully calibrated bubble. Dark energy's acceleration could take on new meaning if space folds back on itself. Even the arrow of time might behave differently in a looping cosmos. The humbling truth: we may be like ants crawling on a Möbius strip, unaware of the twist that defines our world. Until we spot those ghostly echoes in the CMB, or prove they aren't there, the universe's shape remains one of its most intimate secrets. Black holes aren't just cosmic vacuum cleaners, they're existential puzzles wrapped in event horizons. Stephen Hawking's groundbreaking realization that black holes slowly evaporate through quantum particle pairs, now called Hawking radiation, shook physics to its core. But this discovery unveiled a paradox so deep it challenges our understanding of reality itself. When a black hole vanishes, what happens to all the quantum information it swallowed? According to quantum mechanics, information can never truly be lost. It might get scrambled, but it must persist. Yet Hawking's calculations suggested black holes erase it permanently, vanishing like a burnt book with no ashes left behind. This conflict between quantum theory and gravity isn't just about black holes, it's a ghost haunting cosmology, forcing us to ask, If information can disappear in the heart of a singularity, could the same have happened during the Big Bang? Picture a black hole's life cycle as a cosmic magic trick. A star collapses, forming an event horizon, a point of no return where matter and light vanish from our observable universe. Over eons, Hawking radiation siphons away the black hole's mass until it explodes in a final burst of energy. But here's the rub: everything that fell in, the composition of swallowed stars, the quantum states of particles, seems irretrievably lost. This clashes with quantum unitarity, the principle that information evolves deterministically, never disappearing without a trace. It's like saying a shattered vase's fragments contain no memory of its original shape, an idea that makes physicists profoundly uneasy. The resolution might lie in holography, the radical notion that all information within a black hole's volume is encoded on its two-dimensional surface like a cosmic QR code. If true, the information isn't destroyed, it's transformed, scrambled into thermal radiation we don't yet know how to decode. This idea, stemming from string theory, suggests that black holes obey the same quantum rules as the rest of the universe. They're just far better at hiding the evidence. But if black holes preserve information through holographic encoding, what does that imply about the Big Bang? Could the entire universe, born from an unimaginably dense singularity, have preserved its own quantum information in a similar way? Some theorists propose that the Big Bang singularity wasn't an information shredder but a cosmic reset button, a moment where quantum data was scrambled but never erased. Others speculate that inflation's explosive expansion acted like a quantum backup, stretching and imprinting early fluctuations across the cosmos in patterns we now see in the CMB. The echoes of those primordial quantum states might still linger, hidden in the large-scale structure of galaxies or the polarization of ancient light. If we can crack the black hole information paradox, we might unlock clues about how the universe managed its own quantum ledger in those first chaotic moments. What's at stake is more than theoretical neatness. If black holes destroy information, our current laws of physics are incomplete, an unsettling gap where predictability breaks down. But if they preserve it through mechanisms we're just beginning to grasp, the implications ripple backward through time to the universe's birth. Future experiments, like detecting the faintest signatures of Hawking radiation or simulating black hole mergers in quantum computers, could tilt the scales toward one resolution or another. Until then, the paradox remains a stark reminder that the cosmos guards its deepest secrets fiercely, and that even the darkest objects in the sky might hold the keys to understanding how everything began. The holographic principle turns our understanding of reality inside out, literally. What if everything we perceive in 3 dimensions, galaxies, stars, even our own bodies, is actually a projection of information encoded on a distant 2-dimensional surface? This isn't science fiction. It's a serious theory emerging from the crossroads of black hole physics and string theory, with startling implications for how we view cosmic inflation and the very fabric of space-time. The idea traces back to an unexpected place: the event horizons of black holes. In the 1970s, physicist Jacob Bekenstein calculated that a black hole's entropy, a measure of its hidden information, was proportional not to its volume but to the area of its boundary. Stephen Hawking later confirmed this, showing that black holes radiate energy and shrink over time, eventually disappearing. But if information can't be destroyed, where does it go? The holographic principle proposes an elegant answer. All the data about what fell into the black hole is preserved on its event horizon like a cosmic hard drive. Now stretch this idea to the entire universe. Just as a 3D hologram emerges from patterns etched on a 2D surface, our reality might be a projection of information stored on some unimaginably vast boundary enclosing the cosmos. This boundary could be the inflationary horizon, the farthest edge of space that expanded faster than light during the Big Bang's first moments. If true, it means the universe's entire history, from quarks to galaxies, is painted on this primordial surface with our 3D existence as its shadow. What makes this radical concept so compelling is how it solves long-standing paradoxes. For instance, inflation's exponential expansion should have diluted quantum fluctuations beyond recognition. But if those fluctuations were encoded on a 2D surface first, their information would remain intact even as space stretched, neatly explaining why we see coherent patterns in the cosmic microwave background. It also offers a fresh perspective on quantum gravity, the elusive theory bridging Einstein's relativity with quantum mechanics. By treating space-time as an emergent property rather than fundamental, the holographic principle sidesteps the infinite densities that plague traditional models of the Big Bang. Imagine running a video game on a flat computer chip. The game world appears three-dimensional, but its reality is just code on a 2D circuit. Similarly, the universe might render gravity, particles, and forces from underlying data we can't yet perceive. This isn't just philosophy. Experiments like the Fermi Lab holometer have searched for holographic pixelation in spacetime itself, hunting for faint noise that would betray its digital-like structure. Yet the principle raises profound questions. If we're living in a cosmic projection, what or who is the projector? Could other universes exist as parallel holograms on the same surface? And how does consciousness fit into a reality where depth is an illusion? While we're far from definitive answers, the holographic principle has already reshaped cosmology's frontier. It suggests that the universe's deepest truths aren't found in the stars above, but on a hidden canvas. We're only beginning to decode a canvas where the Big Bang's first brushstrokes might still be waiting to be read. While the cosmic microwave background gets all the attention, there's another, far more elusive relic from the Big Bang still hiding in plain sight: the cosmic neutrino background. Born just 1 second after the universe began, these ghostly particles outnumber atoms by billions to one, streaming through your body right now at nearly the speed of light. Yet detecting them is like trying to catch fog with a fishing net. Neutrinos barely interact with matter, passing through entire planets as if they weren't there. But make no mistake, these invisible wanderers were once the universe's dominant force, shaping its evolution in ways we're only beginning to understand. Picture the cosmos at 1 second old, a seething plasma 10 billion degrees hot, where neutrinos outshone every other particle in existence. As the universe expanded and cooled, these neutrinos decoupled from matter, creating a background sea as fundamental as the CMB but far harder to see. Unlike photons, which scattered off electrons to create the microwave afterglow we observe today, neutrinos slipped free without leaving obvious fingerprints. Their background radiation, cooled to just 1.96 Kelvin after billions of years of cosmic expansion, remains the holy grail of high-energy physics, a direct window into the universe's first moments that could reveal secrets no other probe can reach. The challenge: neutrinos are nature's ultimate escape artists. Every second, trillions pass through your fingernail with zero effect. To catch these phantoms, scientists have devised mind-bending experiments. Some, like the Ice Cube Neutrino Observatory in Antarctica, use cubic kilometers of glacial ice as a detector, hoping for the rare neutrino that collides with an atom to produce a telltale flash of blue light. Others propose exploiting coherent neutrinos, scattering a quantum effect where neutrinos might nudge atomic nuclei just enough to be measured. But the real prize will be capturing low-energy relic neutrinos from the Big Bang themselves, frozen in time like insects in cosmic amber. Why go to such extremes? Because the neutrino background isn't just a curiosity, it's a missing piece in our cosmic puzzle. These particles were the universe's first messengers, carrying details about conditions before even the CMB's photons could travel freely. Their exact temperature and distribution could confirm whether inflation really happened, or if exotic particles like sterile neutrinos, hypothetical heavy cousins to the ones we know, existed in the early universe. There's even a wild possibility that neutrinos left subtle imprints in the CMB's polarization patterns, like whispers of their presence etched in light. The hunt is accelerating. Next-generation detectors like the Ptolemy project aim to trap relic neutrinos using layers of graphene and quantum sensors chilled to near absolute zero. Others plan to analyze ancient minerals deep underground, where neutrinos might have left radioactive traces billions of years ago. Each experiment pushes the boundaries of technology, chasing particles that could rewrite our understanding of the Big Bang's first second. What's astonishing is how much we already know about something we've never directly observed. Neutrinos slowed the early universe's expansion rate, subtly altering the CMB's power spectrum in ways that betray their presence. They helped determine how matter clumped into galaxies by carrying away energy that would otherwise have fueled gravitational collapse. And if we ever do capture one, it won't just be a scientific triumph, it'll be like recovering a lost page from the universe's birth certificate, written in a language only the cosmos itself can fully decipher. Until then, these ghostly particles remain both a testament to our ingenuity and a humbling reminder of how much we have yet to learn. The universe's fate hinges on a cosmic tug of war between two invisible forces, dark energy pushing space apart and gravity pulling it together. Right now, dark energy dominates, accelerating the universe's expansion, but will this last forever? The answer lies in deciphering dark energy's true nature, and the possibilities are as dramatic as they are unsettling. Picture a future where galaxies drift so far apart that their light can never reach us, leaving the night sky black and empty. This is the Big Freeze, the most widely accepted scenario. In this slow-motion fade-out, dark energy remains constant, stretching space until even atoms are torn apart by its relentless push. Stars burn out, black holes evaporate via Hawking radiation, and the universe settles into a lifeless, near absolute zero equilibrium, a graveyard of scattered particles too distant to interact. But dark energy might not play fair. What if it strengthens over time? Enter the Big Rip, a far more violent demise. Imagine dark energy as a runaway engine, its repulsive force growing until it overwhelms gravity, then electromagnetism, then even the nuclear bonds holding atoms together. First, galaxies would be shredded, then solar systems, then planets, and finally, in the last terrifying fractions of a second, atoms themselves would explode into disconnected quarks and electrons. The universe wouldn't just end cold, it would end loudly, torn apart from the inside out. Some theories suggest this could happen in as little as 22 billion years, a blink on cosmic timescales. Then there's the Big Crunch, a dramatic reversal where gravity finally wins. If dark energy weakens or decays, the expansion could slow, halt, and then collapse inward like a deflating balloon. Galaxies would merge in a fiery chaos, temperatures soaring until space itself becomes a superheated soup of particles. The cosmos would end as it began, a singularity of infinite density. Strangely, this scenario offers a sliver of hope. Some models suggest a collapsing universe could bounce, triggering a new Big Bang and birthing another cosmos in an endless cycle of death and rebirth. What decides which future awaits us? Inflation's initial conditions cast the first vote. The same quantum fluctuations that seeded galaxies also set dark energy's strength too weak, and gravity would have already reversed expansion too strong, and the universe would have ripped apart before life began. The fact we're here suggests dark energy is finely balanced, but for how long? Observations of distant supernova and galaxy clusters hint that dark energy's density might fluctuate, potentially dooming us to a big rip or offering a reprieve via a crunch. The wild card, quantum vacuum decay. If our universe is just a temporary bubble of stable space-time, a random quantum event could trigger a catastrophic phase transition. a new inflationary bubble expanding at light speed, erasing everything in its path. One moment the cosmos exists, the next it's rewritten by laws of physics we can't fathom. It's a reminder that the universe's fate isn't just about dark energy's tug of war with gravity, it's about the fragility of reality itself. For now, the cosmic jury is out, but every measurement of distant galaxies, every refinement of the Hubble constant, brings us closer to knowing whether our universe will end with a whisper, a scream, or something stranger still. One thing's certain, the same forces that lit the stars are counting down the clock, and the answers are written in the expanding darkness between them. What if the uncanny precision of cosmic inflation, the way every quantum fluctuation, every gravitational balance, fits together like gears in a master clock, isn't just a happy accident of physics, but the signature of something far stranger? The simulation hypothesis takes this eerie perfection and asks a daring question. Could our universe be the product of an advanced civilization's technology, an artificial construct running on some unfathomable quantum computer? Think about the numbers, the universe's fundamental constants, the strength of gravity, the mass of an electron, even dark energy's elusive energy density, are balanced so exquisitely that altering any by a hair's breadth would render stars, planets, and life impossible. This fine-tuning has puzzled scientists for decades. Inflation's near-flawless execution, stretching space just enough to smooth wrinkles without tearing reality apart, feels less like random chance and more like optimized code. Even the cosmic microwave background's temperature variations, down to 1 part in 100,000, mirror the kind of noise you'd expect from a high-resolution simulation's rounding errors. The argument gains traction when you consider how we design a universe ourselves. A sophisticated simulation wouldn't render every atom in real time. It would use shortcuts, just as video games load detailed graphics only when observed. Quantum mechanics, with its reliance on observation and probability, fits this idea unsettlingly well. The double-slit experiment, where particles behave as waves until measured, could be seen as processing power being conserved until a player looks. Even the Planck length, the smallest meaningful unit of space, might hint at a pixelated substrate underlying reality, but here's where it gets thorny. Proponents argue that if civilizations eventually create simulations indistinguishable from reality, the odds favor us being inside one after all. There'd be countless simulated worlds, but only one base reality. Critics counter that invoking unseen simulators explains nothing. It simply kicks the mystery upstairs. Why would a simulation include the suffering of black holes or the tedium of 14 billion years of cosmic evolution? And how could we test the idea without access to the source code? Yet the hypothesis refuses to fade, fueled by discoveries that feel like glitches in the matrix. The axis of evil's eerie alignment, quantum entanglement, spooky action at a distance, even the perplexing simplicity of the universe's fundamental equations, all whisper of a deeper architecture. Some physicists propose looking for literal bugs, anomalies in high-energy particle collisions that might reveal computational limits, or patterns in the CMB resembling error correction codes. Whether cosmic joke or profound truth, the simulation hypothesis forces us to confront how little we understand about reality's scaffolding. It turns cosmology into a detective story where the clues might be hidden not in the stars, but in the pixels of existence itself. And if the universe is a simulation, well, at least the graphics are spectacular. The cosmic mysteries of inflation and the Big Bang aren't locked in the past. They're the focus of a new generation of experiments so advanced they'll peer deeper into the universe's origins than ever before. Leading the charge is CMB-S4, a sprawling network of ground-based telescopes set to scan the cosmic microwave background with unprecedented precision. Imagine upgrading from a blurry black and white photo to a razor-sharp 8K image. this project will map the CMB's temperature and polarization fluctuations 10 times more accurately than Planck, hunting for the faintest fingerprints of primordial gravitational waves. These elusive ripples in spacetime, if detected, would be the smoking gun for cosmic inflation, proving space itself stretched violently in that first trillionth of a second. But CMB S4 isn't just looking for confirmation. It's designed to spot anomalies that could upend our models, like unexpected twists in the polarization patterns that might hint at entirely new physics before the Big Bang. Meanwhile, high above Earth's distorting atmosphere, the Lightbird satellite prepares for launch. This Japanese-led mission specializes in measuring the CMB's polarization across the entire sky, focusing on the large-scale patterns that could reveal inflation's energy scale. Think of it as a cosmic seismograph. By analyzing how space shook during inflation, Lightbird could determine whether the process was driven by a single quantum field or a more complex interplay of forces. The satellite's ultra-sensitive detectors, chilled to near absolute zero, will face an ironic challenge, distinguishing inflation's faint signals from the thermal whispers of the instrument itself. Success would mean unlocking the energy threshold at which gravity and quantum mechanics merged, a realm far beyond what particle colliders can probe. But the real game changers might be the next-gen gravitational wave observatories. While LIGO detects cataclysmic events like black hole mergers, future facilities like the Einstein Telescope and Cosmic Explorer aim to catch subtler tremors, low-frequency ripples from the universe's birth. Buried in this cosmic static could be echoes of inflation's final moments, when the inflatoned field collapsed into the hot soup of the Big Bang. There's even a wild card, space-based detectors like LISA, which could uncover ultra-low frequency waves from phase transitions in the early universe, offering a completely independent test of inflation's timeline. What ties these projects together is their potential to cross-examine cosmology's biggest claims. If gravitational waves, CMB polarization, and large-scale structure all point to the same inflationary model, it would be a triumph. But if they disagree, that's when things get exciting. Contradictions might expose cracks in our understanding, pointing toward exotic ideas like a bouncing universe or higher dimensional physics. Either way, these experiments aren't just tools, they're time machines, giving us front-row seats to the universe's first moments, and the most thrilling possibility. They might uncover questions we don't even know to ask yet. From the cosmic microwave background's whisper to the gravitational echoes of inflation, these 25 discoveries haven't just expanded our understanding, they've rewritten the origin story of everything. We've traced how primordial quantum fluctuations grew into galaxies, how dark energy's invisible push is tearing space apart, and how the universe's very geometry might be a hall of mirrors hiding dimensions we can't yet see. Each revelation peels back another layer of the cosmos, exposing questions even more profound than the answers they replace. Think about how far we've come. A century ago, astronomers debated whether the Milky Way was the entire universe. Today, we're mapping the afterglow of creation itself, decoding the universe's baby pictures, and even speculating about cosmic collisions with other realities. The cosmic microwave background, once dismissed as pigeon interference, is now a time machine revealing the universe's first moments. Dark matter, once a fringe hypothesis, shapes every galaxy we see. And inflation, what began as a scribble on Alan Guth's notepad, has become the cornerstone of modern cosmology, explaining everything from the universe's flatness to the seeds of galaxies. Yet for all we've learned, the greatest lesson might be humility. The Hubble tension's stubborn mismatch, the cold spot's eerie chill, the lithium problem's nagging gap, these aren't failures but signposts pointing toward discoveries yet to come. Science doesn't end with tidy answers, it thrives where mysteries deepen. The same cosmic microwave background that confirmed the Big Bang now hints at anomalies like the axis of evil, while Hawking radiation's paradoxes force us to rethink the nature of reality itself. This isn't the end of the story, it's the prelude. Next-generation telescopes will hunt for primordial gravitational waves buried in the CMB's polarization, while underground labs listen for dark matter's faint whispers. The James Webb Space Telescope is already spotting galaxies so early they shouldn't exist, and quantum computers might soon simulate conditions even the Large Hadron Collider can't reach. Who knows what we'll find? Maybe evidence of a multiverse, or relics from before the Big Bang, or physics so strange it makes today's theories look quaint. So keep looking up, not just with telescopes but with imagination. The universe began in a blaze of mystery, and it's far from done surprising us. Whether you're an armchair cosmologist or a professional chasing the next breakthrough, remember, every answer unlocks new questions, and every night sky still holds secrets whispered from the dawn of time. The cosmic detective story is just getting started, and the next chapter promises to be the most astonishing